Welcome to Lecture 8. This week we're going to cover just one chapter. We're going to be talking about a type of mathematics called graph theory. Often when we're analysing theoretical problems, it's useful to transform the problem into a collection of vertices joined by lines. For example, when he was visiting the city of Königsberg in 1736, the Swiss mathematician Euler was set a problem by the locals. And to solve this problem, he invented a type of mathematics which we now call graph theory. This city, Königsberg, which is now called Kaliningrad, was divided into 4 landmasses by a river. There were 7 bridges across the river joining these landmasses together, as shown in this picture. And visitors were often asked the following problem by the locals. Can a person walk around this town and cross each bridge once and only once? Euler was the first person to solve this problem. And we're going to be discussing how he solved it later. Euler's main insight was it doesn't matter where the buildings are, it doesn't matter where the streets are or the shapes of the river. All that matters are the land masses and how they're joined together with the bridges. Euler understood that we could reduce the problem to this picture. The land masses we can call A, B, and C, and the bridges we're labeling 1, 2, 3, 4, 5, 6, and 7. We only need to be thinking about the picture on the right. Now, for many years, graph theory was just used by mathematicians as a bit of fun, just to solve some interesting riddles and some problems. But nowadays, it's used in many things. It's used in computing, it's used in physics, in neurology, in chemistry, and many other disciplines. So let's start. A graph is formed by points, which we call vertices, and lines, which we call edges. For vertices, we're going to use lowercase letters, A, B, C, etc. The edge, which joins vertex U to vertex V, we're going to write like this. We're going to call it open bracket U, comma V, close bracket. U and V we call the end points of the edge E. A non-empty set of vertices together with a set of edges is called a graph. An edge which starts and finishes at the same vertex is called a loop. So, for example, this is a graph. This graph has 3 vertices, those are the 3 blue triangles, and it has 4 edges, the 4 red lines. One of these edges, the one at the bottom right, starts and finishes at the same vertex. This is called a loop. You might be given a question like this. Let V be the set containing 4 vertices, which are labeled A, B, C, and D, and let E be the set containing 5 edges, E1, E2, E3, E4, E5. Edge 1 joins A to B. Edge 2 joins B to C. Edge 3 joins C to D. Edge 4 joins A to C. And edge 5 joins B to D. Draw this graph. First thing to do is to draw the vertices, and it doesn't matter where we put them. I might put them like this, A, B, C, D. I could swap the positions of 2 of them, it doesn't matter. Maybe I swap C and D around. Maybe I want the vertices in a line, that would be okay. Maybe I want to just draw them like this, it really doesn't matter. I'm choosing to draw these 4 vertices in a square. Then we need to draw the edges. First of all, edge 1 joins A to B. So we draw it. This is edge number 1. Next edge 2, joins B to C. So let's draw that. Edge 3 joins C to D. Edge 4 joins A to C. And edge 5 joins B to D. And then we're finished. This is a picture of the graph that we were asked to draw. Sometimes we have two edges which have the same endpoints. These are called parallel edges. If we have a graph which does not have parallel edges and does not have loops, then it's called a simple graph. Let's go back to this example. We're asked to draw a picture of this graph. And this is the information that we have. First, we're told that there are 4 vertices, and these are called A, B, C, and D. And we're told we have 5 edges, called E1 up to E5. First, let's draw the vertices. And it doesn't matter how we draw them or where they're drawn. Just draw 4 circles any way that you want, like this, or like this, or like this, or like this. Draw them however you want, it doesn't matter. Then we need to draw the edges. Let's go back to the information that we have. Edge 1, we're told, is an edge which joins A to B. So here we go, A is joined together with B, and then just to label it, this is E1. We change to a different color. The next piece of information in the example is E2 is the edge which joins B to C. So let's draw it and let's label it E2, and so on. The third one, E3. The question tells us that E3 joins C to D, so we draw that. The question tells us that E4 joins A to C, so let's draw it. And the question tells us that E5 joins B to D. So again, let's draw it. And then we're finished. We've drawn the 4 vertices and we've drawn the 5 edges. As I said before, 2 edges which have the same endpoint are called parallel edges. About arrows, we'll talk about that later, not for this type of graph. If we have a graph which does not have parallel edges and does not have loops, then it's called a simple graph. This graph has parallel edges. Look, there's 2 edges which join B together with C. This edge joins B to C and this edge joins B to C. These are parallel edges. If a graph contains parallel edges, then we call it a multigraph. If we let the graph have both loops and parallel edges, then we call it a pseudograph. If E is an edge, E from U to V is an edge, or a graph like this, an undirected graph, then we say that U and V are neighbors. In this picture, A and B are neighbors, but A and V are not neighbors. There's not an edge from A to V. The degree of a vertex is the number of edges connected to that vertex. When we're counting the degree of a vertex, if we have a loop, we count that as 2. So, for example, give the degrees of all the vertices in this graph. First, let's look at A. How many edges are connected to A? There's 2 edges. So the degree of A is 2. How many edges are connected to B? We can count them. 1, 2, 3, 4. The degree of B is 4. The degree of C is also 4. The degree of D is 1. There's only 1 edge connected to D. I'll skip E for the moment. The degree of F is also 4, and the degree of G is 0. Let me ask you, what is the degree of vertex E? So, 3 people correct answer, 13 people weren't able to answer. The degree of E is 3. There's 3 edges connected to E. Another one, give the degrees of all the vertices in graph H. The degree of A is 3. The degree of B is 6. The degree of C is equal to 1. The degree of D is 5. And the degree of E is also 5. Now remember, when we have a loop, we count it as 2. So 1, 2, 3, 4, 5, 6. The degree of B is a 6. A vertex without an edge, in other words, where we have degree equal to 0, is called an isolated vertex. In this picture, G is an isolated vertex. A vertex of degree 1 is called a pendant. Pendant has only 1 edge. In this picture, vertex D is a pendant. The first theorem of today, let G be a pseudograph. That's a graph where we're allowed to have parallel edges and we're allowed to have loops. and let NE denote the number of edges in the graph. Then the theorem says if we add up all of the degrees of the vertices and then divide by 2, we get the number of edges in G. For example, a graph has 10 vertices and the degree of each vertex is 4. How many edges does the graph have? We use the theorem. The number of edges is a half multiplied by the sum of the degrees. So it's a half multiplied by 4 plus 4 plus 4 plus 4, etc. A half multiplied by 40 or 20. We can say that this graph must have 20 edges. Now, so far, all of the graphs have been undirected graphs. That means that the edges don't have directions. If we wanted to, we could change each of these edges to an arrow. If the edges in a graph have directions, then the graph is called a directed graph or digraph. If a directed graph has parallel edges, then it's a directed multigraph or multi-digraph. This is a picture of a multi-digraph because we have parallel edges just here. In a graph, all of the edges are going to be the same type. So they're either going to be all directed or they're going to be all undirected. Let G be a directed graph. Now, if we write E is the vertex from U to V, then the order of U and V is important. This means the edge which starts at U and it finishes at V. We can talk about degrees in a directed graph, but we have to have two types of degrees. An in degree, that's the number of edges coming into V, and an out degree, that's the number of edges coming out of V. If we have a loop, we count it as 1 for both the in degree and the out degree. Find the in degree and out degree of every vertex in this graph. Let's look at A first. I'm only interested in the edges which are coming into A. Only the arrows which point towards A. I'm only counting these two. The in degree of A must be 4. So what am I talking about? The in degree of A, I'm getting ahead of myself, must be 2. There's 2 arrows coming into A. How many edges go out of A? There's 1, 2, 3, 4. The out degree of A must be 4. A question for you. What is the in degree of C? And what is the out degree of C? The in degree of C is 3 and the out degree of C is 2. We have another theorem. Let's suppose we have a directed graph, and let NE be the number of edges in G. Then the number of edges in G is the sum of all the in degrees, and it's also equal to the sum of all the out degrees. Let's go back. How many in degrees do we have in total? 2 plus 2 plus 3 plus 2 plus 3, 12. How many out degrees do we have? 4 plus 1 plus 2 plus 2 plus 13. Again, 12. A simple graph which includes all the possible edges is called a complete graph. In a complete graph, every vertex has an edge with every other vertex. A complete graph with n vertices is denoted by Kn. And the degree of every vertex in Kn is going to be n minus 1. So that means that Kn must have n multiplied by n minus 1 divided by 2 edges. For example, the complete graph with only one vertex is called K1. The complete graph with 2 vertices is called K2, and so on. Next idea, the idea of a planar graph. A planar graph is a graph which we can draw in the plane or on a piece of paper in such a way that the edges intersect only at the endpoints. In other words, the edges don't cross over. So for example, look at this graph. The way we've drawn it at the moment, there's 2 edges which are crossing over. But we can rearrange this. Remember, it doesn't matter the shapes of the edges. It doesn't matter where we put the vertices on the paper. We can move them about any way that we want. And for this graph, we can move the vertices and the edges around like this in such a way that the edges don't intersect. So then this must be a planar graph. Sometimes we can't do this. Sometimes we have a graph which can only be drawn without intersecting edges in 3-dimensional space. This is called a 3-dimensional graph. This graph, for example, I've tried to draw it so that it looks like the edge from A to C is somehow above the edge from B to E. This is not a planar graph. It's not possible to rearrange this graph in such a way that we don't have intersections. The next idea is the idea of a cycle graph. It's probably easier if I show you the pictures. Cycle graph C3 has 3 vertices and they're joined together like this. We have an edge joining 2, and then we go to the next vertex and then to the next vertex, and so on. This is cycle graph C4, cycle graph C5, cycle graph C6, and so on. If we take a cycle graph, Cn, if we add another vertex in the middle and then join that to all of the other vertices, then we have a graph which is called a wheel graph. Now, the notation is a little unusual here because W5 has 6 vertices. We still call it W5 because we made it by starting with C5 and then adding another one in the middle. A bipartite graph is a graph where these wheel graphs don't have any intersecting edges because we've added an extra vertex in the middle and then none of the red lines are crossing over each other. Next idea, a bipartite graph. The idea here is we can split the set of vertices into 2 distinct subsets. And we do this in such a way that every vertex in V1 connects to a vertex in V2. In other words, we don't have an edge from a vertex in V1 to another vertex in V1. In a bipartite graph, there's no edges going from V1 to V1 or going from V2 to V2. So for example, the graph C6. Last time I drew this as a hexagon. But we don't have to draw it like that. We could rearrange it like this. And then we can see that if 3 of the vertices we say are green and 3 of the vertices we say are orange, every edge joins one of the vertices in the green box to one of the orange ones. There are no vertices joining 2 vertices in green, and there are no vertices joining 2 in orange. Another example, is this graph a bipartite graph? We can answer this problem using 2 pens. What we're going to do is we're going to pick one of our pens and we're going to pick one of our vertices. It doesn't matter which vertex we start with. Let's just say that I pick my orange pen and I want to start at B. Doesn't matter where we start. Let's say that, and let's suppose we color in this vertex orange. Then I'm going to switch to my other pen. I'm going to pick up my green pen and I'm going to color in every vertex which is a neighbor of B, every vertex which is connected to B. So for example, there's an edge joining B to C, so I'm going to color in C. B is also connected to E, I'm going to color that green, and B is connected to F, so I color that green. Now, are there any green vertices connected together? Is C connected to E? No. Is C connected to F? No. Is E connected to F? No. So far, we're okay. Let's go back to the orange pen. Every vertex which is connected to a green vertex, I want to color in orange. So I'm coloring in D and A orange. Let's just check, are any of the orange ones connected together? No. Back to the green pen and color in the final one, green. Using these 2 colors, we've colored in the vertices in such a way that the green ones are not connected to each other. There's no vertex, there's no edge from a green to a green, and the orange ones are not connected together. There's no edge from an orange to an orange. That means this graph is bipartite. We can perhaps see this more clearly if we redraw the graph like this. Put all of the orange ones on the left and all of the green ones on the right, and then draw exactly the same edges that we had before. I'll leave it for you to check that this graph is the same as the previous one. every edge goes from the left to the right. Every edge goes from an orange vertex to a green one. So this graph is bipartite. Let's do another one. Is this graph bipartite? Again, we'll choose a pen and we'll choose somewhere to start. And color it in. Let's say I color in D green. And now I switch to my orange pen and I'm going to color every vertex which is connected to D in orange. But look, I have orange connected together with orange. So now I know that this graph is not bipartite. Let's talk about walks. Now we're going back to the problem we started with, where Euler was asked about walking around Königsberg. A walk is a list of vertices and edges. It goes vertex, edge, vertex, edge, vertex, edge, and so on. And it's done in such a way that every time we write an edge, the edge connects the two vertices together. So edge 1 connects V0 with V1 and so on. So for example, look at this graph. Let's suppose we want to start at A. We go from A to B, from B to E, from E to D, up to C, to F, to G, and then back to F. We can write this walk like this. I'm starting at A, so I write A first. I use E1 to get to B. So A, E1, B, that's the first part. Use E5 to get to E. So that's this part. I'm going to use E4 to get to D. So I write E4D and so on. This is a walk in this graph. An Eulerian trail is a walk which satisfies two rules. Rule number 1, no edge is repeated. And rule number 2, every edge is included. So for example, I'm saying that this walk, written down here, is an Eulerian trail. I'm saying that all of the 10 edges appear in this list one time and only one time in this list. Let's see what we have. We're going to start at D. We're going to use E5 to get to E. And then we use E6 to get to A. And then we're going to use E7 to get to F. E8 to get to B. And then we go to A. And then we go down to D, to C, to G, to B, and then back to C. This walk has every edge in it once and only once. So this is an Eulerian trail. The Königsberg bridge problem, which we started with, can be rephrased as, does there exist an Eulerian trail in Königsberg? Not quite ready to answer that, but we will do soon. A graph is connected if there exists a walk between every pair of vertices. So for example, graph H here is connected. Choose any two vertices. Let's suppose we choose B and D. It's possible to walk from B to D. Graph G is not connected because it's not possible to walk between G and A. Time for a theorem. Let G be a connected graph. Then there exists an Eulerian trail if and only if the number of degrees of the number of vertices of odd degree is either 0 or 2. And furthermore, if G has 2 vertices of odd degree, then the Eulerian trail must start and finish at these 2 vertices. For example, let's look at K3 and K5. In K3, the degree is 2, degree is 2, the degree is 2. Every vertex has even degree, because 2 is an even number, so there must exist an Eulerian trail in K3. Likewise, in K5, the degree of every vertex is 4. So there must exist an Eulerian trail in K5. But in K4, the degrees are all odd numbers. Degree is 3, the degree is 3, the degree is 3, the degree is 3. There's 4 vertices of odd degree, so there does not exist an Eulerian trail in K4. Go back to this one. The degrees are 4, 4, 3, 3, 2, 2, and 2. So that's even, even, odd, odd, even, even, even. There's 2 vertices of odd degree. That means there must exist an Eulerian trail, and it must start and end at C and D. We've already found this one, and we know that that's true. Now let's go to Königsberg. Now that you know this, can you answer this problem which stumped people for many, many years? Count the degrees of the vertices. How many of them have odd degree? Okay, so the degree of A is 3, the degree of B is 5, the degree of C is 3, and the degree of D is 3. There's 4 vertices of odd degree. So what does that tell us? So the theorem says there can only exist an Eulerian trail if the number of vertices of odd degree is either 0 or 2. But now we have 4 vertices of odd degree, so that means there does not exist an Eulerian trail in Königsberg. That means it was not possible to walk around the city of Königsberg and cross each bridge once. I have one more idea before we finish. The idea of Euler's formula for polyhedra. Now, Euler's formula is the number of vertices minus the number of edges plus the number of faces. So for example, let's talk about a cube. How many vertices does a cube have? How many corners? 1, 2, 3, 4 on the top, and then another 4 on the bottom, so that means 8. How many edges does it have? 1, 2, 3, 4 edges on the top, another 4 on the bottom, and there's 4 vertical ones. So there's 12 edges. How many faces on a cube? 6, we know that. So let's do number of vertices minus number of edges plus number of faces. 8 minus 12 plus 6, and we get 2. Euler's formula for a cube gives 2. Let's do another one. A tetrahedron. How many vertices are there? 4. How many edges? We count them on the picture. 1, 2, 3, 4, 5, 6. And how many faces? 4. And then we do Euler's formula, number of vertices minus number of edges plus number of faces. And we get 2 again. Maybe that's a coincidence. Let's try again. A pyramid. A pyramid has 5 vertices, 8 edges, and 5 faces. Number of vertices minus number of edges plus number of faces is 2 again. Let's go again. This shape is called a dodecahedron. Dec means 10, and do means 2, so it's 10 plus 2 or 12. I'll leave it for you to check that there are 20 vertices, 30 edges, and 12 faces. Euler's formula, 20 minus 30 plus 12 gives us 2 again. That's 4 shapes in a row, and we've always got 2. That's suspicious. Let's look at a football, an old type of football. I have 12 pentagons and 20 hexagons. How many vertices are there? Well, we can calculate this because every vertex is on a pentagon, and there are 12 pentagons. And each pentagon has 5. So the number of vertices must be 12 multiplied by 5. Or there must be 60 vertices. How many edges are there? Every edge joins together 2 vertices, and every vertex has 3 edges. So I'm going to do 60 vertices, multiply by 3, because each vertex has 3 edges connected to it, but then we're counting each one twice. So I'm going to do divide by 2, or 90. How many faces are there? 12 pentagons and 12 hexagons. Add them together. 12 plus 20 gives us 32. And then what's Euler's formula going to give us? 60 minus 90 plus 32 gives us 2 again. Now, if we have one of these polyhedra, it's a polyhedra which doesn't have any holes in it, is Euler's formula always going to be equal to 2? And if that's yes, how can we prove that it's always equal to 2? Let's think of it like this. Let's go back to the cube. What I'm going to do is I'm going to take the cube and I'm going to remove one of the sides. Let's say we take the top off and we're going to throw the top away. And then I'm going to stretch and squash the cube flat. Now, what have we done so far? We've removed one face. We haven't changed the number of vertices and we haven't changed the number of edges. So we still have 8 vertices and we still have 12 edges. And we have 1, 2, 3, 4, 5 faces. If we also count the outside, then that will account for the one that we removed and threw away. We can think of a cube like this. We can do that for all of the shapes. The tetrahedron, we can think like this. Both the tetrahedron on the left and the graph on the right have 4 vertices, 6 edges, and 4 faces. If we count what's outside the graph as one of the faces. Pyramid, 5 vertices, 8 edges, and 5 faces. Or this shape, this letter T. I'll leave it for you to check later that there are 16 vertices here, 24 edges, and 10 faces. Every one of these 3-dimensional polyhedrons is equivalent to a connected planar simple graph. Let me remind you, simple means there's no parallel edges and there are no loops. Planar means we can draw it on a piece of paper without any intersecting edges. None of the edges cross over. And connected means that we can walk between any 2 vertices. So the idea is, if we know something about these graphs, then we also know it about polyhedra. And this is something we do in maths a lot. We change a problem into a completely different problem. We solve the different problem, and then we know something about the first problem. So what do we know about these graphs? Let's start with the first complete graph. This is K1. 1 vertex, 0 edges, and 1 face. We can do Euler's formula for this graph. 1 minus 0 of 1 is equal to 2. So this one at least satisfies that Euler's formula is equal to 2. Next, let's think about any connected planar simple graph. Just draw something. Draw some vertices on a piece of paper and join them up in such a way that there's no parallel edges, there's no loops, there's no intersecting edges, and make sure that all of your vertices are connected. Now, how can we make this simpler? There's a pendant vertex up at the top left. We could cut this off. What happens if we cut this off? Well, the number of vertices goes down by 1 because we've removed a vertex and we've thrown it away. The number of edges also goes down by 1 because we've cut off this vertex and we've thrown it away. But the number of faces stays the same. So it's going to be -1 for the number of vertices, minus -1 for the number of edges, and then +0 for the number of faces. But that's 0. If we cut off a pendant vertex like this, then Euler's formula does not change. What else can we do? We could cut one of the edges. What happens to the number of vertices if we cut this edge? Nothing. The number of vertices will stay the same. What happens to the number of edges if I remove this edge? The number of edges goes down 1. What about the number of faces? That also goes down 1, because now we're joining together what was 2 separate faces and now joined together to be 1. So Euler's formula stays the same. 0 minus minus 1 plus minus 1 or 0. This is something else that we can do without changing Euler's formula. So let's keep doing this. Let's keep making this graph simpler. And every time we do one of these steps, Euler's formula doesn't change. We can remove this one, this pendant vertex. I can cut an edge, remove a pendant vertex, and so on. Keep simplifying this. And every time I do this, Euler's formula is not changing. And I just get left with the trivial graph, K1. The graph I started with must have the same value for Euler's formula as this one. So the graph I started with, which was any graph that I drew, must have Euler's formula is equal to 2. That proves that if G is a connected planar simple graph, then Euler's formula is always equal to 2. And the same is true for polyhedra without holes. And that brings us to the end of this week's lesson. This is the end of our 3 lessons about finite mathematics. Next week, we're going to start talking about calculus. Are there any questions? Okay, so if you think of a ring donut, something which has a like that, then that has a hole in it. If I drew this picture, think about a donut. There's a hole here. If we had something like this, then Euler's formula is not 2. If we drew some vertices on the surface and we connected them together somehow, we would get a number which is not 2. In fact, we would get 0 for this. If we have something which doesn't have a hole in it, so for example, we have a cube or any of these other shapes which I was drawing, then we always get that Euler's formula is 2. So for example, I could draw one vertex just here to an edge which goes all of the way around like this and joins up like this. And then I could have another edge which goes all of the way around like this. Then the number of vertices is going to be just 1. The number of edges is going to be 2. And the number of faces, if you think about this, if we cut along all of these lines, there's just one face just here. So then we will get 1 minus 2 plus 1 or 0. If we have a solid object in which we can't stick our finger through a hole in the middle, and if we drew vertices and edges on the surface, then we would always get Euler's formula is equal to 2.